Hey YouTube, I was thinking more about diffraction and decided to go into a little bit more detail as to why it happens on the surface of my hard drive. In a normal transmissive diffraction grating, white light comes in and is dispersed into its component wavelengths. Longer wavelengths like red light are bent more, whereas shorter wavelengths like green and blue are bent less and less. And some of the white light passes straight through. In order to understand why this is happening, we have to think about what's happening at that surface of the diffraction grating. We're going to start by thinking about what happens when light of one wavelength passes through a single hole in that diffraction grating. In these diagrams, I'm going to show light in a couple different ways. Just as an arrow pointing its direction, as a squiggly sine wave to show the wave-like nature of it, or as these vertical parallel lines, which are like looking down at that wiggly sine wave, but from the top. As the red light reaches the single hole, it radiates out the other side, acting like a point source of light. Light coming from this point source goes more or less uniformly in all directions. If we look at two of these slits side by side, they act like two point sources, very close together. Each one radiates light outward more or less uniformly. But as these two light sources radiate outward, their light overlaps with each other. You'll see that there's many places where these waves cross over. Places where the light waves cross at peak to peak or valley to valley, they interfere with each other constructively. This means that their two waves add together. When they meet valley to peak, they destructively interfere, negating each other. If you allow the light that's passed through these two slits to fall upon a screen, you'll find that it forms light and dark spots. These are points where the light either constructively or destructively interferes. If you were to graph the intensity across the width of the sheet, it would look like this. These areas of varying intensity happen at different angles for different wavelengths of light. Now that we've seen what happens with light from two slits interfering with each other, let's see what happens with a diffraction grating where you have light from many slits interfering with each other. Just like the double and single slit, light radiates from all of these slits in all directions, but we're going to look at it as it leaves in one particular direction because of something interesting that happens. For this particular angle and for this wavelength of light, if you were to draw a line from one slit to the ray of light coming from the next slit, making sure that that line meets the ray of light at right angles, you would find that it would land on the other ray of light at the same point in the wave's phase. This sounds a little complicated, but I'm going to draw it here. This means that it takes light coming from one slit, one full wavelength, to get to that point that's at right angles if you draw a line to the next slit. This means that light from both slits are in phase with each other. Just like the example with two slits, this means that the light with this particular wavelength, leaving those slits at this particular angle, will constructively interfere with each other. If you allow this to fall upon a screen, you would notice that there would be a bright spot of this color falling on the screen. If you continue to draw these lines at right angles from one ray to the next, you'll notice that they will land on the next ray with this same one cycle displacement. That means the light from every ray at this particular angle constructively interferes with the light from all the other rays. So now we know that light passing through a grid of slits of a certain wavelength and radiating at a particular angle will all interfere with each other constructively. If you were to extend this, you would find that at steeper angles the light would interfere at more than one wavelength intervals, so it might be 2 or 3 wavelengths before the light interferes, but the end result would be a series of light patches of that particular wavelength of light. If we were to do this experiment with blue light instead of red light, you would notice that the light radiating at a different angle would interfere constructively. This is because blue light has a shorter wavelength, and so the light doesn't have to be tilted quite as much in order to get that one wavelength displacement from one ray to the next. Other than the exact angle, everything else would be the same as with the red light. Each ray would be displaced by an integer number of wavelengths from the wave next to it, allowing them to all interfere constructively when they fall upon a screen. If you were to pass both red and blue light through the same screen, you would notice a red dot and a blue dot at different places on the screen. This is because the red light and blue light only constructively interfere at particular angles. Passing white light through the same screen would cause a rainbow to be shown, because each wavelength of light only constructively interferes at one particular angle. This is a very simplified way of thinking about how a transmissive diffraction grating works. The difference between this and the surface of my hard drive is that the hard drive is acting like a reflective diffraction grating. When we look closely at the surface of the hard drive, you could see that the surface was covered in many ridges. When light falls onto these ridges, it radiates out in all directions as it is reflected. This makes each of these ridges act like a small point-like source of light. The light from each of these different point-like sources interferes with the light from each of the other point-like sources, causing this diffraction effect. On a professionally made reflective diffraction grating, the surface has a very particular profile in order to cause these point light sources to exist. In this hard drive, however, it's accidental, so the diffraction effect is not very pronounced, but it is still just a little bit visible. I hope you found this video interesting. If you'd like to see more like this, check out my channel. Thanks for watching.